Many research studies follow a model typically used in the physical sciences that relies upon hypothesis testing. You may recall from very early in the course that a hypothesis is simply a testable proposition about the relationship between variables. For example, do teachers who graduated from accredited colleges of education earn higher salaries in their first years in the classroom compared to those who graduated from an uncredited institution? Or are men more supportive of capital punishment than women? Or finally, is the proportion of Hispanics who attend church services higher than the proportion who attend services for the population overall? The null hypothesis is denoted H0, which we pronounce as H0. It represents the idea that there's no relationship between the variables. The alternative hypothesis is denoted by H1. It represents the notion that there is a relationship. Let's start by taking a look at a study designed to test the hypothesis that first-year salaries for teachers in general are different than the salaries for those that graduated from an accredited college. Based on already existing national data set, we find that the mean first-year salary for all teachers is $36,000. If our sample mean is different than $36,000, then we reject the null hypothesis. If not, then we fail to reject the null hypothesis. This language is very important because we never prove or disprove a hypothesis. Because the findings of individual studies are always tentative, prove or disprove are terms that we don't use. We either reject or we fail to reject. Okay, so now we go out and select our sample of first-year teachers who graduated from a non-accredited college. It turns out that the mean for our sample is $35,990. Do we reject the null hypothesis? $35,990 is certainly not equal to the value in our null hypothesis. Yet, despite this clear difference between these two values, most of you would agree that we probably should not reject. Take a moment to think about why you wouldn't want to reject the null hypothesis based on this sample mean. Intuitively, I think that you know the answer. But what about a sample mean of $35,500 or $34,000 or $33,000? How different, in other words, would our sample mean need to be in order for us to agree that it made sense to reject the null hypothesis? Let's take a step back. We've drawn a sample and observed that it's different from our expected sample of $36,000. There are only two possible reasons for this. The first is that the sample we've selected of teachers who graduated from non-accredited colleges was, purely by chance, not representative of the population of all teachers who graduated from non-accredited colleges. Maybe our sample happened to include only teachers in the South, where wages are lower across the board. Maybe it consisted of teachers who graduated with unusually low grade point averages. With a large enough sample, this is unlikely, but it is nonetheless possible. Of course, the other possibility is that there is in fact a difference in starting salaries. In order to make sense of this, let's take a look at the sampling distribution. Remember that in order to use the properties of sampling distribution, we need to convert the mean of the sample we select to z-values. That's why the horizontal axis of this distribution shows z-values. We know that 68% of all the samples we might select have a mean that's within 1 standard deviation unit of the standard error of the true population mean, and that 95% are within 2 standard error units of that mean. If our sample mean falls to the right of this value or the left, we'll take the view that it's so unlikely to be due solely to chance that we'll make a decision to reject the null hypothesis. The question really is this: what's the likelihood of observing the mean of our particular random sample if the null hypothesis is in fact true? If that likelihood is very small, then we reject the null hypothesis and accept the alternative as the more reasonable explanation for the sample mean that we've observed. If the likelihood is not very small, then we just chalk up the difference in the sample mean and the population mean to chance, and we fail to reject. That, more than anything, is what hypothesis testing is all about. Now, there are, of course, a few details we need to fill in. The first and most obvious is this: how unlikely does a sample mean have to be to reject a null hypothesis? In most social sciences, we reject a null hypothesis if the mean of the sample we've selected is more than about 2 standard deviations from the population mean, which in this example is about $36,000. That's the same as saying that we will reject a null hypothesis if there's less than a 5% chance that the sample we selected would have the mean we observed if in fact the null hypothesis was true. In some cases, researchers will reject only if there's less than a 1% chance of selecting a sample with that mean. These likelihoods are denoted with the Greek letter alpha. I know you want to get into solving some problems, but there are 2 more things that we need to cover. The first has to do with the difference between hypotheses that look like these and hypotheses that look like these. In the first case, we need to conduct what's called a two-tailed test. What this hypothesis states is that the mean for non-accredited graduates is different from that of all graduates. It could be more, it could be less. We don't know. And for that reason, we have to allow for the possibility of both a smaller and a larger sample mean. To do that, we divide that probability of 0.05 and distribute it across the 2 tails of the distribution. If we have a sound theoretical reason for believing that non-accredited teachers earn less, then our hypothesis would look like the one on the right. In this situation, we need to perform a one-tailed test. At alpha equals 0.05, we reject means, sample means, that fall here. I'll just point out, which hopefully is obvious if you think about it a bit, that it's harder to reject a null hypothesis with a two-tailed test because the sample mean has to be further away from the population mean. In a one-tailed test, on the other hand, that 5% probability is lumped over on one side of the distribution, which has the effect of moving the associated sample mean closer to the population mean. Let's take a closer look at this. Again, in a two-tailed test, we need to divide that 0.05 probability that our sample mean is not representative into 2 parts. In a one-tailed test, where we have a theoretical reason for believing that the sample mean will be greater or could be less, but in this case it would be less, we don't divide that 5% area. This has the effect of moving the sample mean we would need to reject the null hypothesis to the left. Of course, if our alternative hypothesis was that the sample mean was less than the population mean, then we'd move the required sample mean to the right. In either case, it becomes easier to reject the null hypothesis since, again, the sample mean doesn't have to be as different from the population mean as in the instance of a two-tailed test. All right, one last point. Suppose we set alpha equal to 0.05. We select our sample and find that its mean falls outside the range of rejection. There's still a 5% chance that our null hypothesis is in fact true. Again, maybe we just happen to draw an oddball sample. That sample that contains teachers with mostly low GPAs or who are teaching in a low-wage state. Of course, we can never know if the null hypothesis is actually true or not. But if the null hypothesis is in fact true, and our sample mean nonetheless falls out in this region over here, then we've committed what's called a type 1 error. A type 2 error occurs in the opposite situation. A type 2 error occurs when we fail to reject a null hypothesis that's in fact false. This kind of error is a bit harder to explain. Let's start out by pointing out that if our null hypothesis is in fact true, then our sampling distribution will look like this. If it's false, and in fact teachers actually do make less if they graduated from a non-accredited school, sampling distribution will look like this. So we draw a sample and find its mean is located here. With this sample mean, we'd reject the null hypothesis. But this turn of events is called a type 2 error. A type 2 error occurs when we fail to reject a null hypothesis, which is in fact false. As I'm sure you can see, if we set alpha at say 0.01, we decrease the likelihood of a type 1 error because the level we need to reject is more extreme. At the same time, however, we increase the chance of a type 2 error. This table summarizes type 1 and type 2 errors. It's important to remember that we never actually know whether our null hypothesis is in fact true. When we say that a finding is statistically significant at alpha equals 0.05, all we're actually saying is that there's only about a 5% chance that we would have selected a sample with that mean, with the mean we calculated, if in fact the null hypothesis was true. The word error here takes on a different meaning. It doesn't mean that we made a mistake, we've calculated something incorrectly, and so on. The term error, as we use it here, means that our test of statistical significance simply failed to reveal the true relationship between our variables. There's nothing in these statistical techniques that says anything about what is actually true or false. Whether a proposition is true or false can only be arrived at over time by consensus after many studies and much replication. At the end of the day, there's nothing we can do about this. That doesn't mean that it's not important, however. The possibilities of these errors drives home the idea that we're dealing here with probabilities and chance. Understanding and managing chance is what inferential statistics is ultimately all about.